We got 11 panelists now. Couple more coming.
Good morning, everyone. We're going to wait just a minute or so while all of you attendees are joining the meeting, and then we'll get started. Okay, great. Good morning, and thank you for joining this session on model development. My name is Ben Murphy, and I'm a physical scientist at the US EPA Office of Research and Development in Research Triangle Park. I'd like to introduce my co-chair this morning, Professor Zhang in the Department of Civil and Environmental Engineering at Northeastern University. I know many of you know her and her impressive history of contributions to the air quality modeling research community very well. So it's our delight to bring you a number of really interesting and exciting talks this morning. We have a truly diverse lineup of science topics to discuss. So I'd like to get to that as soon as possible. But first, I'd like to share an outline of today's session. Oops, too far. Okay, so first, I'd like to remind everyone to please submit your live questions to the talks that hopefully you've had a chance to look at already. Through the Q&A chat, we'll be monitoring those and delivering them to the speakers throughout this 1-hour session. We have 14 presenters who we will introduce shortly, and we hope you've had an opportunity to see their presentations already. We will give each presenter a minute or so to refresh the audience on the key messages of their talk. Then we will take a few moments to answer specific questions that have been put to them by you or by us. So again, please submit your questions to the Q&A panel. We apologize that we likely will not have time to get to all or even most of the questions that we receive, but we hope that this platform will give you an opportunity to connect afterward to the questions that we weren't able to get to. If time permits, as we go through this panelist lineup, we'll also pose some more general kind of panelist level questions that everyone can contribute to. And hopefully these will kind of connect multiple presentations together. So we want to emphasize that all panelists are invited to comment on these questions, even if they haven't given their kind of brief 1-minute presentation summary at that point. So without further ado, let me introduce our panelists. First, we have Ross Beardsley from Ramble, Brian Berman from Drexel University, Patrick Campbell from the NOAA ARL Air Resources Lab, Xiaoyang Chen from Northeastern University, George Delich from Hyperism Consulting, LLC, Chris Emery from Ramble, Sichi Ma from NOAA ARL, Gavindra Pandey from the University of North Carolina, Chapel Hill, Elise Pennington from the California Institute of Technology, Armin Puyai from the University of Houston, Yuha Tang from NOAA ARL, Jose Tirado Delgado from NOAA NWS Office of Science and Technology Integration, Kai Wu from the University of California, Davis, and Shuping Zhang from the University of Chinese Academy of Sciences. So thank you everyone for joining us this morning. We're really looking forward to an exciting conversation. I'd like to start off our talks with Ross Beardsley from Ramble and give him an opportunity to refresh us on his presentation and his key messages from his talk titled Revision 5 of the Carbon Bond 6 Mechanism, CB6R5. Ross?
Morning all. As the title states, my talk was on the 5th revision of the Carbon Bond 6 Mechanism, or CB6R5. We completed this work recently with sponsorship from the Texas Commission on Environmental Quality. In this revision of the CB6 mechanism, we prioritized updates in 3 ways. The first was the top 50 parameters in Carbon Bond 6 revision 4 that were determined to contribute to uncertainty in ozone production. This was determined in a recent study by Alan Dunker, Greg Garwood, and others. The second was reactions involving simple inorganics such as NOx, OH radicals, and odd oxygen radicals, many of which have not been reviewed or updated since the initial release of CB6 in 2010. And last was reactions of simple organic compounds with oxidants. In total, we reviewed 152 reactions, 47 of which were updated. We did not end up modifying the chemical species. So luckily for all of you emission folks, there's no changes to emissions or boundary conditions that are required. We did end up adding one reaction. The addition of this reaction was to account for a recent finding by Midro et al., in which they found that water vapor accelerates the reaction of the OH plus NO2 reaction rate. We used a simple implementation in CB6R5 to account for this acceleration. And then we tested this revision using the TCQ modeling platform for a period of high ozone in June of 2012 in Texas. Overall, we found that the revisions to the mechanism resulted in slightly higher ozone and NO2 over land and slightly lower ozone and NO2 over the Gulf of Mexico. We also performed a simple model performance evaluation for ozone and found that CB6R5 performed similarly to CB6R4 for monitors in Texas.
Perfect. Thank you, Ross. And so with just about a minute or two, would you mind addressing this first question? So did any other chemical species besides ozone and NO2 change dramatically, such as pan or glyoxal? And did you have observations to compare to other chemical species besides ozone?
We actually did change pan somewhat significantly. I think that was in the top 50 reactions that we looked at, contributing to ozone uncertainty. The changes to pan generally led to an increase in ozone production. So yes, that was changed. If you want to see in detail what specific reactions were changed, you can look at the full report, which is available on the TCQ. Regarding what observations were compared, we only did a simple MPE for ozone. This will likely occur in the future. We would do a more detailed evaluation, but for now, all we've looked at is observations of ozone.
Great. And how about this second question? So what's the likely reason for the NO2 reductions over the Great Lakes and coastal New England waters? And would you expect these over other colder water bodies?
We didn't look in that detail. Our focus was primarily on Texas. Part of that is likely caused by the reaction we added to increase the OH plus NO2 reaction in the presence of water vapor. So I think anywhere you have high concentrations of water vapor, you'll see this reduction. But a number of other things can be attributed to that as well. I'd have to dig into that more to answer that specifically.
Okay, great.
And then we have two live questions. And the first one, live questions.
Terrific.
And the first one, did they change hydrogen peroxide prediction?
I'm not sure on H2O. We did see increases in OH. I'm not sure about hydrogen peroxide.
Okay, the second question here, I heard about two versions of CB6R5, D1 and D3. Which one did you use?
So we used a combination of those. Actually, what we did here is we implemented a number of different changes to different groups of reactants like PAN or NO2, and then we ultimately decided on a combination mechanism, which was based on the evaluation of these different versions of CB6R5. And if you want to see what was in the different versions like D1 and D3, you can see that in the full report.
Terrific, thank you. Let's move on to our next speaker. And just as a reminder to all of our panelists, please mute your lines when you are not speaking. Wonderful. Our next speaker is Elise Pennington from the California Institute of Technology. And we invite her to share a few words about her presentation, A Model to Represent SOA Formation from Volatile Chemical Products. Elise?
Great, thank you. So I was using the newest version of CMAQ, version 5.3.2, and updated it to include chemistry from volatile chemical products, or VCPs. These are organic compounds emitted from a wide range of consumer products. And so in the results that I presented here, I looked mostly at VCP IVOCs and developed 3 new pathways to represent their SOA formation. These 3 pathways are for siloxanes, other oxygenated IVOCs, and non-oxygenated IVOCs. And our preliminary results in CMAQ show that these increase the SOA by up to about 2 micrograms per meter cubed.
Wonderful, thank you, Elise. And let's take this first audience question here. So have you tested the model in a region where SOA is not significantly underpredicted? Are you sure that you're not just adding mass to the system in an unconstrained way?
Yeah, so we have not looked at the results in an area where SOA isn't underpredicted so far. We're in the fairly early stages. We've just been looking at Los Angeles. But we know that these VCPs are important in urban areas at least. And so I would say probably we would hope that the emissions would capture this difference, because typically SOA is more accurately predicted right now in less urban areas. And so where we would expect to just have fewer emissions from VCPs. And since these are completely new surrogates, it wasn't a revision to the existing gas phase mechanism, we would just probably see in those areas less mass going into these new surrogates. But that's definitely something to look at.
Wonderful, thank you. And I'll just put this other question to you that I had. So are there other specific classes of compounds, kind of more specific than, say, oxygenated IBOCs, for instance, like siloxanes, but maybe ones that haven't gotten quite so much attention that you foresee we might need an explicit approach for, maybe because they are good tracers or have unique chemistry or particularly high contributions?
So I would say maybe glycol ethers, just because that is another sort of subclass of compounds that chamber studies are looking at as VCP tracers. But many of the oxygenated compounds have a lot of different functional groups. So less clear how to define those into a specific explicit class.
Gotcha. Thank you. All right, thank you, Elise. So we'll move on to our next presenter, George Delich from Hyperism Consulting, LLC. And we asked George to give a 1-minute reminder of the takeaways from his presentation, CMAQ 5.3, Parallel Performance for a 101-Day Simulation. George?
Okay, can you hear me?
We can hear you. Yeah.
Okay. I've been doing this for probably over a decade, putting OpenMP threads into CMAQ versions as they come along. And this time I opted, with the help of some people at EPA, to do the whole 2016 scenario. And so far I've only gotten the first quarter done. And I'd like to acknowledge Kirsten Foley, Ed Anderson, and Liz Adams for their help in getting the data. I decided also to include all 3 CTM solvers, EBI, Rosenbrock, and GEAR. And the GEAR is still in progress. The main result is that there are speed-ups, but a little bit less than I expected. And I think I know the reason for that, and I'll come back to that at a future date. But the speed-ups range from about 1.16 up to about 1.25 for GEAR, the last one. I'm expecting more from GEAR, and I'm looking into that. That led me in the debugging process to look at species concentrations, and there is something wrong with the GEAR solver in CMAQ 5.3 as released by the EPA. And that is different from what it was in 5.2. I'm tracking that, Ben, and I will give EPA a summary of my findings when I get done. But the progress is on track. We are getting speed up, and now we have a threaded version of the Rosenbrock solver, which runs in about the same time that the EPA's EBI solver runs. So I'm recommending that that replace the EBI solver. And one day I hope EPA will issue a contract for that work. I'll gladly take questions.
Wonderful, thank you, George. Let's start with some of the audience questions. So for the heterogeneous system in your presentation, how many cores are there in each node?
There's, well, total core count is 192, but it's spread over 3 generations of CPU CPUs. The 2 head nodes have dual 16-core CPUs. There are 8 HP blade servers with 8 cores per node. And then we recently added this year 6 more blades with 12 cores per node. There's a slight bottleneck in the last 2. When we do the OpenMP runs, we distribute generally 1 MPI process appropriate to the number of cores there, but they have to double up on the last two nodes, which may be a bit of a bottleneck. And we're going to do another upgrade to replace that. If you want the real look at table 2.1 in the long write-up, it's got a lot of gory, boring detail there.
Okay, thank you very much, George. In the interest of time, I think we will move on. And here we are. I had a panel question here directed at this idea of kind of connecting with Ross, Elise, and George together and thinking about how we may be extending chemical mechanisms in the future with increased detail in chemistry for sources like VCPs, for example, and what that would mean for the development of mechanisms and then the increased potential runtime for computer models. However, I think we don't really have enough time to get into it at this point. I do want to kind of put it there so the speakers can maybe kind of think about some potential answers if we have some time to come back to it. But I'd like to move on for now to our next speaker, Chris Emery with Ramble, and ask him to share a few details from his presentation, new features and updates in CMAQ version 7. So Chris?
Yes, hello all. CMAQ 7 was a major update. We hadn't had a release of CMAQ for about 2 years, which is fairly long for our release frequencies. So I would say the largest updates in CMAQ 7 were associated with I/O. We've moved all the I/O to netcdf format. And particularly using netcdf4 with data compression via HDF5. And so that really does compress file formats quite effectively, and there's no need for external manipulation. Several other updates. Emissions are more flexible now. You can add however many emissions files you want. Multiple input files for gridded. We added 3D gridded emissions. We have multiple point source emissions for point sources as well. And these can be a mix of the new netcdf format or the traditional Fortran binary. We have some probing tool updates with I/O as well that allows for one-way nesting of source apportionment applications. Science update would be the adding of the bidirectional ammonia deposition emission scheme from Zhang et al. 2010. We have some SOA updates. They were more of adjustments than really updates to the science. Adding DMS chemistry, adding elemental species to be parallel with CMAQ AE6. I mentioned the source apportionment updates for one-way nesting and some tie-ins back to getting DDM fully operational for particulate matter. And we'll have some further updates in version 7.1 this winter.
Unmute myself. Thank you so much, Chris. So I had well, maybe one specific and one more general question from your presentation. And I think I'll focus on the second one, the more general one, if that's okay. Given all the excellent updates that you summarized in your presentation in here, I was wondering if you would share with us perhaps the kind of now future near-term and long-term challenges that you see for further CMAQ development. But where are you guys going from here?
Yeah, I would say that we're keeping an eye on state of the science for chemistry, primarily, as Ross talked about in CB5 or CB6R5. We have plans for CB7 coming probably over the next year. We're certainly keeping an eye on SOA. That's continually evolving science, as we've already seen so far this morning. And then ammonia bidi. That seems to be a fairly large influencer of PM simulations, particularly, I would say, east of the Rockies more than west, but there seems to be some significant sensitivity there, so we're looking at that. I would say those are the major challenges as we move forward. I would say overall, boundary conditions are continuing to be a major I would say, importance for inputs to the photochemical model, especially in the West, where there is a large, particularly for ozone, background coming in from the rest of the world, and how to characterize that properly to get improved performance in Western urban areas in particular, or even Western background areas for national parks and rural areas. It is important. So I would say those are the biggest challenges.
Wonderful. Thank you. All right. Our next speaker is Shuping Zhang from the University of Chinese Academy of Sciences. And we'll invite her to share some thoughts on her talk titled Significant Contributions of Heterogeneous Reactions to the Nitrous Acid Formation During Winter in Beijing, China. Shuping?
Hello, Ben, thank you. In my work, we compare the CMAQ model prediction with measured Hono concentration in Beijing, China for January 2015. The model with the existing Hono chemistry severely underestimates and the observed Hono concentration with the NMB of negative 90%. We revised the Hono chemistry in the model by implying 6 additional heterogeneous reactions in the model, including the reaction of NO2 on the ground surface, reaction of NO2 on the aerosol surface, reaction of NO2 on salt surface, the photolysis of aerosol nitrate, nitric acid displacement reaction, and hydrochloric acid displacement reaction. The model with the revised chemistry substantially increased Hono prediction and improved the comparison with observed data with an NMB of -5. The photolysis of Hono enhanced the daytime the OH by almost a factor of 2. The enhanced OH concentration compare favorable with observed data and produce additional sulfate by reaction with sulfur dioxide, aerosol nitrate by the reaction with nitrous dioxide, and the secondary organic aerosol by the reaction with VOC. The additional sulfate improves the comparison with observed concentration. However, it doesn't close the gap between the model prediction and the observed data during the plotted days.
Wonderful, thank you. I was wondering if you could comment on one of the parameterizations in your model, the one for the ground surface reaction to form Hono. I think I understood from your presentation that you referenced a 2003 paper, Vogel et al., I believe, for the parameterization there and used different factors for urban versus, I assume, forest surface types. And I was wondering if all of that's accurate, how much uncertainty there is in those parameterizations and what impact that has on your results. How much more work needs to be done there to understand what appears to be that very important pathway?
Yes. Firstly, I will answer the question of the the difference from the urban to the forest. Based on our results, the NO2 heterogeneous reaction from the ground is the most important reaction, but the parameter of the ground aerosol density is based on the leaf arrow index. But the emission from the forest arrow is likely lower than the urban arrow. For example, for the average Hono in the after we implant the new reactions into the CMAQ, the average Hono in the urban area increased 1 or 2 ppb, but it doesn't have obviously change in the forest area. I think the reason is the emission from the forest area. The NO2 emission is too low in that area. The second question is about the uncertainty of my parameterization. Actually, yes, all these parameters are very sensitive, and I have shown the parameters I have used in the slides. For the And I also have some sensitivity runs, and I will publish them in my paper. I only make one example for about the aerosol nitrate fertilizer rate. If I use the 30 that's the result in our slide. If I use the 100, that will be tripled. The whole node will increase from 0.5 to 1.9 at the node. And so that's a large difference.
Oh wow, yeah, that's a lot to deal with.
Yeah.
Okay, thank you very much. I think we will press on to our next speaker, Brian Berman from Drexel University. And he posted his presentation titled Modeling Indoor Aerosol Thermodynamics with Isoropia. And so Brian, if you would like to share some thoughts, go for it.
Yeah, so my work, so summary of my work is I expanded upon an organic indoor model that was developed by Cummings and Waring in 2019 to focus on modeling inorganic indoor aerosols of outdoor origin. I did this by incorporating the thermodynamic model Isoropia, and this is the first time that this has been done in an indoor model. Then to evaluate this model, we used data input from a study that looked at how the variation in outdoor aerosol concentrations and composition impacted indoor aerosols, and compared our model results to these observed results. And overall, we saw good sulfate matches. There was a slight underprediction of summertime nitrate and an overprediction of ammonium. However, the winter time results for nitrate and ammonium didn't look as good, and we think this could be contributed to not having real gas phase data to work with, and also possibly not fully capturing wintertime HVAC thermodynamics. So that work is currently ongoing.
Thank you very much. I noticed somewhere in your presentation, you also mentioned potential interferences with third-hand smoke. And I was wondering just how many people would you need, or kind of what would need to be the magnitude of that source in order to cause the kind of interferences with your evaluation that you saw?
Yeah, so that's a good question. And so like third-hand smoke is like the residue of tobacco smoke that absorbs onto indoor surface and clothing. So the number of occupants might not matter as much as like how many smokers there are, or like what the surfaces are made of. I'm not really sure how large of a contribution we would need from this in order to get a better match for the summertime ammonium. But what we're trying to do is derive a way to calculate the equivalent ammonium concentration due to third-hand smoke, and then so that could be like removed from the current modeled summertime results. But as I was saying before, there could be like other factors that are driving this overprediction, such as like the thermodynamics from the HVAC or not having real gas phase data. So it's something we're exploring. I'm not entirely sure yet.
Excellent, excellent. Something for us to wait for, to anticipate. Wonderful. Our next speaker is Kai Wu. Here we are, from the University of California, Davis. Is Kai online? I'm not seeing his video in my view. Is he here? Okay, I think we don't have Kai. So I'll just mention a couple of, or the kind of high level message that I remember from Kai's presentation. And I encourage everyone to, of course, go and see it and reach out to Kai with any specific questions that you have. He and his co-authors looked at the uptake of ammonia to secondary organic aerosols for some applications, or for some time periods in China, some particular pollution episodes. And as I recall, I think they used a factor of 10% conversion or something along those lines to kind of divert the ammonia away from equilibrium with the inorganics to forming these kinds of, I guess, amine compounds, but they're quite neutral. They're not they're not very important for looking at gas particle partitioning for the other inorganic species. So I'm not going to butcher his message too much more than that. Hopefully that gives those of you who are interested a bit of a more enticement to go in and check out his presentation and follow up with him. And with that, we will move on to our next speaker. I'm going to do a quick time check here. I think we have a couple of minutes actually to maybe take a pause. And I'd like to go back to the panel question that I posed here in the context of VCPs. But since we've already kind of gone through most of the first half of our speakers, I would like to kind of broaden this a little bit and look for feedback from all of our panelists about this kind of overall question of increasing complexity in chemical mechanisms that we put into either large or fine scale models, and thinking about how we can, how we need to introduce these details in a way that kind of gives us the best of both worlds in terms of accuracy, but also computational efficiency. That's a very broad topic, but if anyone has some thoughts they'd like to share on that, please take the floor.
Oh, okay. I can't resist an audience. So George here. Sorry, George here, if I can respond. To reduce large runtime costs, use an open MP threaded version of CMAQ, and adding more species or more reactions only increases computational intensity, i.e. more work per thread, which will enhance speed up. So don't feel inhibited when you think of adding species or reactions. There is a path forward which can reduce the wall clock time.
Okay. I guess I'd also like to pose this question more directly towards Ross and Chris to maybe put them on the spot. And based on your experience, are there types of reaction mechanism cycles or groups of species that are more expensive than others? So if we're adding 10 or so VCP derived SOA precursors that only interact with OH, for example, and make some SOA condensables, is that cheaper than adding some important components to expand NOAA chemistry and take into account more of the Hono chemistry that Xuping was discussing?
Chris, do you want to speak to that? I don't really know if I can speak to runtimes of different groups of compounds.
No, I'm not the chemist. I think Dr. Greg Yarwood, who manages our chemical updates, would have a much better handle on this. So perhaps as a follow-up, if you really have interest, we could, you could email Greg, and he might be able to answer these questions much better than Ross or I.
Okay.
But certainly, there's always updates to second organic aerosol chemistry that we're interested in. I think moving forward, particularly with CB7, we may start looking at nitrates and compounds like that. So certainly balancing runtime, but there's things like SOA chemistry has become increasingly important. And it's something you'll likely see more so in CB7 than CB6R5.
Okay, terrific. And maybe just one other kind of arm to that conversation, as we're thinking about increasing complexity on the chemistry side, we can of course also be thinking about increasing complexity in terms of particle morphology. And so I wanted to kind of turn the question towards Brian and perhaps Xuping, and thinking more about how important are we starting to find it that we need to start taking into account multi-phase chemistry in larger scale models, and is it becoming too critical to ignore things like core shell morphology in chemistry, or are those issues that that we can still kind of simplify until later and we have more information?
Thank you. As I know, I did this homework with SOA in EPA. As I know, he tried made this place on Alaska, and he said that it also has a big difference for the Hono and the secondary components stimulation in that area. So I think that's the my thinking about this part.
Yeah, thank you very much. All right. I think with that, we can move on to our next speaker, and I will shift things over and hand off control to my co-chair, Professor Zhang.
Hi, Ben. Thank you. All right, our next speaker is Amon Poya, and from University of Houston, who has been developed an integrated Lagrangian model, and that's based on O'Leary's CMAQ model. Amon, would you mind summarize your work in a few minutes?
Thank you, Dr. Zhang. So we implemented a Lagrangian advection scheme called the trajectory grid into the CMAQ O'Leary framework. With this, we were able to follow the trajectories of air parcels as well as the concentration of air pollution. So C-Trail can be a practical tool for studying the impact of long-range transport and species concentrations over a receptor. For evaluating our model, we chose the CORSIQ campaign over East Asia, and the C-Trail result showed how in some days, long-range transport was responsible for increasing carbon monoxide concentrations over Seoul, South Korea. And our work has been recently published in GMD journal.
Thank you. You sort of addressed the first question, so I have questions here. Have you had the chance to compare the results from C-Trail and SM, which is source apportionment technique within CMAQ?
Yeah, so no, we have not compared the result of C-Trail and ISAM because yeah, C-Trail is in its first stage of development. We hope that in someday in future, we will be able to add aerosol module and emission tagging to our model. And also the quantitative comparison between these two models, I think it's kind of not meaningful because they are different in different levels. Yeah, I think that right now it's not possible comparing these two, but in future, probably yes, we will compare this.
Thank you. And what is the actual CPU overhead and by running C-Trail comparing to CMAQ? Okay,
the issue with the C-Trail is that because it's based on a Lagrangian advection scheme, so implementing the parallel computing for a Lagrangian-based model is a relatively hard task. We currently don't have parallel computing for C-Trail, but when comparing them, the C-Trail and CMAQ in a serial mode, the C-Trail is faster because it solved the advection equation once for all the species. Instead of moving through for each species, it solves it only once, and it makes it faster.
Thank you. Let's move to the next speaker. Ben, could you run to the next slide? Thank you. And next presenter is Gavenger Pandey from University of North Carolina, chapter here. And his work focuses on impact of atmospheric stability on air quality around the airport. Gavenger, would you mind summarize your work in a few words?
Thank you. Hello, everyone. This work is one of the key findings of our ongoing FA project, in which we are developing a new airport dispersion model. As all we know that the impact of airport operations on air quality is a key public health concern for the population surrounding an airport, and an added complexity occurs when the airport is situated near a shoreline, where meteorological conditions are far from being spatially uniform. On this condition, to get the better results, we need to give the more realistic data to the model. To illustrate this, here we used widely used regulatory dispersion model, AirMod, And the key findings of our work is metrology matters a lot. And apart from this, MET is not only a factor, there are some other factors such as source characterization, how we characterize the aircraft sources such as area, volume, or line, and the inclusion of rise of these aircraft sources and the limited treatment of chemistry. And all these issues we are trying to incorporate in our new airport dispersion model, which is we are developing.
Thank you. We have a pre-submitted question here. Are the neutral meteorology and roughness length changes based on meteorology observation, or are they idealized adjustment? And if they are idealized adjustment, how do you know you are getting improvement for the right reason?
Yes. These adjustments are based on the meteorological observation. We have modified the MET outputs from the air MET to count the formation of the internal boundary layer, where stable air flows from the ocean on the warmer land of the airport surface. So we have replaced the stable and convective conditions by neutral conditions, as the Lax airport is next to the shoreline. So it never really gets unstable or very stable due to the cold breeze from the ocean towards the airport region. And this can be easily seen by one of my slides in which we have represent the wind roses. And the second change in the roughness length, when the winds are blowing from the northeast quadrant to reflect the flow passing over the tall buildings of the Los Angeles city, and it will affect the roughness length.
Thank you. In light of time, can we move to the next slide, please? Since the first generation of air quality model developed in late 70s, and there have been multi-generations, roughly one generation per decade. And the current trend is a couple of a meteorology and chemistry model. Now another trend is multi-function model or hybrid model. So here is a panel question addressing that. And could Lagrangian model like C-trail and fine scale plume dispersion model that discussed by the first two speakers be used to evaluate each other, or are there too many inconsistency to make quantitative comparison meaningful? So I'd like to come back with this panel discussion if we get time at the end. And this is the question for everybody to think about. And thank you. Our next speaker here is Patrick Campbell from NOAA, ARL, and also George Mason University. And Patrick, would you mind summarizing your work in 1 minute?
Sure, Dr. Zhang, thank you very much. So for the key points of my presentation are really the development of the next National Air Quality Forecasting Capability, or NAQFC at NOAA. And this is based on the Finite Volume CubeSphere Global Forecast System, GFS, version 16. And that's the meteorology that's going to drive the offline coupled state of science CMAQ model, version 531, over the US domain at 12 kilometers. The offline coupling of GFS and CMAQ is done using what we call the NOAA EPA Atmospheric Chemistry Coupler, or NAQ for short. And this is a meteorological preprocessor that's adapted from the US EPA MSIP version 5, which is usually used for WRF. The NAQ CMAQ system is based on GFS. It also includes a number of additional science advancements from NOAA ARL, including real-time rapid refresh of land cover information, advanced windblown dust and wildfire smoke emissions, and also a dynamic aerosol lateral boundary conditions from a NOAA operational global atmospheric composition model, GEFS aerosol. We also aim to improve the community science applications of GFS 16 and the NAQ CMAQ system as an option to running WRF CMAQ.
Wonderful. Could you address one question from audience? Have you done the comparison between NAQ CMAQ and also WRF CMAQ to see which one does better job, in particular in the regions having large surface heterogeneity for complex terrain?
Yeah, this is a good question. I think one that brings up a bigger and more important point. But first, we have not yet done this in any great detail. These runs we compared are using, again, the direct interpolation from GFS 16 to NAQ-CMAQ at approximately 13 kilometers. And that's compared to the, and then a 12-kilometer CMAQ run that's compared to another 12-kilometer WRF CMAQ run. So it would be difficult to really show some of the differences in the complex terrain at these resolutions, but and I would assume that NAQ-CMAQ at 12 kilometers is really still not resolving some of the complex flows in those regions. So I think the best answer to this question, we should probably go further and run a downscaled 3-kilometer WRF CMAQ simulation and compare those regions and complex terrains and flows against a NAQ-CMAQ direct interpolation at 12 kilometer and see the differences. So I think that should be some of our potential future work to highlight this. So at this point, I would say downscaling WRF CMAQ is still the model to use for offline, finer scale, less than 12 kilometer atmospheric composition applications. But it's a great question and something we should explore.
Thank you. I'd like to see that happen in the future through your
Yes.
future talk. All right, let's move to the next speaker. Dr. Yonghua Tang from NOAA, ARL, and also George Mason University, and who's going to talk about this national air quality forecasting capability.
Yeah, this one. Yeah, thank you, Dr. Zhang. This one is part 2 of our presentation. Actually, I just follow up with the Dr. Campbell's question. So we are focused on the verification. And in this effort, you see, we try to develop a method, use GFS directly drive CMAQ instead of use WRF downscaling. So we test that, it looks good. The result is comparable with the WRF downscaling results. Also, it can do much faster. We parallelize the MSIP, the NAQ system. So it can finish the metrology conversion like in 4 to 5 minutes for 3 days. That's much faster than original MCIP. So we use the system to test kind of a lot of kind of configuration of CMAQ like L6 versus L7 and biodi ammonia, etc. And try to find the best configuration for our operational usage. But in general, the new system with CMAQ 531 is much better than our existing system. So we plan to replace the existing NAQFC and the operational system with the new system. So that's our goal. We will continue to turn the system and to see what's the best configuration to be used in our operational. Yeah.
Wonderful, thank you. And could you address one audience question? Are there improvement in the GFS FV3 CMAQ test primarily due to the PBS scheme in the model?
I would say PBS scheme have big influence on this difference, because we saw the GFS yield a higher PBO during daytime, during summer, and lower at early morning. So that a difference effect, like say, the GFS yield a higher surface wind, lower 2-meter temperature. So it's of course is generally lower the PM 2.5. No, lower ozone, but PM 2.5 is varied in most places. The F3 has a higher PM 2.5 than the WRF CMAQ. Yeah. But in correlation, actually, WRF yield better results for the PM surface PM 2.5 prediction. So there's some pro and cons for the system. That's really to figure out why. Yeah.
Thank you. Let's move to the next presenter. Siqi Ma from NOAA Air Resources Lab and also George Mason University. She has also been working on this national air quality forecasting system by improving ozone and nitrogen dioxide. Siqi, could you summarize your work in a few words, 1 minute?
Yeah, thank you. In this study, we conduct a high-resolution 3-kilometer simulation over the Long Island Sound area using the methods like dynamic BC, adjust IC with optimal interpolation, and emission adjustment to improve the model performance. And the results show the methods work and are able to improve the ozone and NO2 performance. And the dynamic BC contributes significantly to this improvement. And the simulation with the multi-adjustments is the best performer during the ozone episode.
Thank you. And there's one question from audience. Do you think the mixed response in NO2 is the result of uncertainty in your methodology, chemistry, or the meteorology?
Yes, I think the uncertainties in the CMAQ model, like the vertical mixing or the sink or deposition of the NOx emission, is one of the reasons of these NO2 results. And in addition, the uncertainties of the input data, like the IC, DC, is another reason. For example, during the IC adjustment, we use the ratios between the surface adjusted and unadjusted concentration to tune the concentration in each vertical level. It's kind of a simple method, maybe leads to the discrepancies of the NO2 simulation. And
great, thank you. Our next speaker is Jose Tarodo Delgado also from NOAA, and he has been working on this NAQFC as well. And Jose, could you summarize the key points from your talk in a minute?
Thank you. Yes, the key message from my presentation is that our team at NOAA is hard at work upgrading our current operational system. As Patrick and Joha already mentioned, we are developing a new coupler, the NOAA EPA Atmospheric Chemistry Coupler, NAQ. We are working on coupling CMAQ with the new NOAA Dynamic Core FE3 based GFS. We are finally going to extend our prediction to 72 hours from 48 hours at the request of the air quality forecasters. We are going to update our fire emission scheme, the global biomass burning emissions, using the global biomass burning emission product extended. And we are also going to upgrade our boundary, lateral boundary conditions using the newly implemented global ensemble forecast system.
Thank you. I do have a few questions for you, but in light of time, let me focus on the high-level question. Given your experience for the model development at NOAA, what are the major science policy considerations for the next generation national air quality forecasting model development?
Well, we make upgrades to our system based on several criteria. Like we listen a lot to the air quality forecasters, the state air quality forecasters, who are our primary customers. And we actually held, every year we have air quality forecasters workshop where they show us a summary of their forecasting activities for the year, and they give us feedback on how our model is performing, and we make upgrades based on those feedback. And we also make upgrades when kind of like Congress requests give us more money. And like right now, the Congress awarded NOAA money to improve all aspects of wildfire research, including wildfire emissions. So those are some examples of how we make decisions about future updates and development.
Thank you. I'm glad you raised a question regarding wildfire emission forecasting. I'd like to come back to that if we got a couple minutes as a panel discussion topic. Our next speaker is Dr. Xiaoyang Chen from Northeastern University. And Xiaoyang, could you summarize your work in a few words?
Oh, thank you, Dr. Zhang. Yeah, sure. Hello, everyone. Our study mainly focuses on the comprehensive evaluation of the experimental air quality forecast system, which you can see there here that couples the global forecasting system version 15 with the CMAQ version 5.2 in an offline manner. This study period covers the year of 2019 and overcomes some major biases in temporal and region-specific performance are found here. And then the system has a overall good performance in ozone forecast skills, but with some moderate overprediction near the Gulf Coast during the ozone season. And it has mixed performance in the PM2.5 predictions, especially for the significant overprediction during the cooler months. These major biases and their potential underlying causes are discussed and for supporting the further development of the NOAA's national air quality forecasting capabilities. Thank you.
Thank you. And there are two quick questions from audience.
Yeah.
The first one was your work, one long-term annual simulation or several short-term focused simulation?
Oh, yeah, and it is from several short-term forecast simulations, and each forecast cycle is 72 hours, and then we conducted the 12 UTC every days, and then we combine these forecast simulations together to into a whole year evaluation.
All right, the second question is about the emission module, GBB EPX. How do you add this emission to the model? Do you use yesterday emission to focus tomorrow's air quality?
I think the Dr. Yonghua Tang would be the best person to answer this question, since the GBP EPX fire emissions was provided by him, and maybe and I'm not sure I can answer this question very sufficiently for you.
Thank you. And let's, we have probably a couple of minutes here. Can we move to the panel question? In light of the ongoing California wildfire that caused record high unhealthy air in a large area, and what are the current focusing scale for extreme events such as wildfire and dust storm, and what can be done to improve the scale? And are there any suggestions, comments from our panelists? In particular, a group at NOAA, and we are all the panelists here. We have 4 members from there. Are there any ongoing work to improve the wildfire focusing you are aware of? You'd like to discuss the key points?
Yes, this is Patrick Campbell. We are continuing to improve our forecasting of wildfire smoke emissions and dust emissions. For wildfire smoke, as Jose alluded to, and we may have touched on, we're using the new GBB EPX product from NOAA for fire detection, and we base our wildfire smoke emissions on directly from the fire radiated power. Shows to be a good proxy, good metric for smoke emissions, and I think our skills in forecasting wildfire emissions have improved considerably. What are we doing currently and trying to improve? Well, I think a major part of our improvement is to discern between different types of fires and the smoke emissions that they create, including agricultural burns versus agricultural fires versus forest wildfire smoke emissions. And so that is a difficult task, but we are working on that. And for dust, we include new really inline advanced FUNCSA windblown dust emissions, and these are strongly tied to the soil characteristics. And we find that that is actually, it's a more highly simplified model that we can tune quite easily outside of the code to better predict dust storm events, both small scale and large scale inside the domain. So those are some of the things we're working on. But of course, you know, again, the major challenge is to do this across scales, and we are currently working on our new inline system, which hopefully eventually the long-term goals will be maybe going down to a finer resolution than what we currently run at. And that's a priority for our NAQFC.
Well, thank you. That's wonderful. Great to know all those ongoing work to address the national priority. And before we close the session, Ben, do you have any comments? Hello, Ben.
Trying to come off mute.
Oh, okay.
No, just to thank everyone for their participation, to thank you, Yang, for your collaboration with me on this, and to thank our organizers, BH, Sarov, Brian, and others who have worked to put this virtual opportunity together.
Well, we should also thank our participants here. We have about 170 people here. Thank you so much for staying with us. And I'll welcome back for the afternoon session.
Wonderful.
All right. Thank you.
Thank you.
Bye-bye.
So long. Goodbye.